Hello, this is Ahmed Ghazy, and I'm pleased to be here today to talk about OpenLANE, an open source digital ASIC implementation flow. This paper has been authored by myself and Professor Mohamed Shalan. So I will begin today's presentation with an introduction explaining the context in which the project has emerged, and discuss the two main use cases of OpenLANE, specifically in micro-hardening and system-on-a-chip integration. In both cases, I will touch upon issues that we faced in the way of full automation, as well as the solutions that we developed in response. I will also talk about the process of synthesis or design exploration and where to find benchmarks in the case of micro-hardening. And I will also showcase Strive 2A, fully automated member of the Strive family of chips. And finally, I will conclude with final remarks and some of the future and ongoing work going currently in the project. So the OpenLANE project started at the intersection of several unprecedented open source efforts, most notably the back then ongoing work to open source a manufacturing ready PDK, and the ever maturing EDA tools from logic synthesis to placement and routing to physical verification and so on. These tools, which are mainly developed by OpenRoad, Open Circuit Design, US's headquarters, are also augmented by a number of other custom tools and scripts that extend their functionalities. And the way all of these tools are used defines the methodology of the flow. As mentioned, OpenLANE can be used for two intertwined use cases, micro-hardening and system-on-a-chip integration or chip assembly. Micro-hardening is a process of taking a design from its hardware description language view into the corresponding various physical views of the manufacturable mask layouts. There are multiple purposes of hardening a design before instantiating it in a containing design, and these reasons include simply reusability, since one can harden the design once, run all of the verification checks like DRC and LVS, and simply have a reusable block to be used any number of times in bigger designs. Another reason is that the micro being hardened may not be simply possible to flatten inside a bigger design, due, for example, to it using a different standard cell library with incompatible side dimensions, being powered using a different power domain, or incompatibilities like that. The second use case, SoC integration, is the process of taking the user's soft macros, as well as other hard macros like SRAM blocks, and place them within a generated pad frame with the right dimensions, as well as generate the power routes and hooking up the macros to the power pads, and finally doing signal routing. If you think that the layout on the right looks chaotic, then that's because it was chaotic. It had manual interventions and placement of macros and their pins was not optimal. The power routing was done completely by hand, but most of the work in OpenLANE on the SoC integration flow was mainly the process of eliminating all manual interventions and cleaning up this layout, which is now on the left, of the first member of the Strive family, Strive, and producing this much cleaner looking layout of Strive 2A. This one uses a 1 kilobyte block SRAM, which was compiled by OpenRAM. And as you can see, the layout, the top level looks much cleaner. The power routes are much more regular. The signal routes are mostly straight lines as compared to all sorts of interesting things going on at the top of the first Strive's chip. So with that introduction, we can now talk about macro hardening flow. So this is a non-interactive flow that runs by default in OpenLANE. And of course, most of these steps are configurable, and one can use interactive scripts to run the steps in custom order or achieve any custom objective. The flow can be divided into roughly 4 steps. First, RTL synthesis and static timing analysis using US's, APC, and OpenSTA. Second, the insertion of DFT structures using Fault. This step is of course optional, and its integration into OpenLANE is still a work in progress. This is then followed by physical implementation of the synthesized netlist we got from US's. A lot of this happens within the OpenRoad app. This is then finally followed by post-routing evaluation of the layout we got. And finally, if everything's fine, streaming the layout into GTS2 format. Since a lot happens in the physical implementation step, I will focus on this next. As mentioned, physical implementation is done using tools within the OpenRoad application, and timing optimizations are done using Brown University's OpenFison. We're getting particularly good results with pin swapping and buffer insertion. These results can be seen on our benchmarks that are shared directly on our GitHub repo, and I will share a link to the benchmarks shortly later in this presentation. Also, logical equivalence checks are done every time the netlist changes by a tool. So for example, every time clock tree synthesis happens or OpenFison runs an optimization, the netlist changes, and so we run logic equivalence check to confirm that the current netlist is functionally equivalent to the previous one, tracing all the way back to the original synthesized netlist. There are also custom tools that were developed to support more use cases than the ones provided by default in the tools. For example, there are two additional very useful use cases during I/O placement. The first one is context-aware I/O placement, which takes into account the context in which the macro being hardened was instantiated in a bigger design. This was particularly useful for SoC integration, and we're going to talk about it later. The second one is specification-based I/O placement, which is intended for cases where there is a strict macro interface required, that is, a specific strict ordering and placement of pins needed. So here you can think, for example, of hardening FPGA fabrics. And finally, there are scripts to implement antenna avoidance methodologies, which is what I'm going to discuss next. So broadly, there are three techniques to mitigate the antenna effects. Two of them are dependent on antenna-aware routing, and those are bridging to the highest metal layer as close as possible to the polygate in RISC, as well as swapping routing layers in order to keep the highest metal layer used in the route, the one closest to the polygate in RISC. And the second one is the insertion of antenna diodes on vulnerable sinks. Since antenna-aware routing wasn't the main goal back when the routers were being developed, the first two techniques, bridging and swapping routing layers, required a lot of development, and hence we opted for diode insertion-based solutions, which I'm going to discuss three strategies for that we use in OpenLANE. First, the obvious brute force solution, which inserts diodes on all polygates, and of course, the pros of this technique is it eliminates most antenna violations, but the cons are also obvious, which are wasted area, posing limit on the core utilization, increasing the capacitive load on all nets, basically, making the circuit power hungry and making it much slower. An improvement to this strategy is to only reserve the space needed for diodes, and instead of inserting diodes in the first place, we insert what we call a fake diode, which is a custom fill cell that has the exact footprint of a diode cell, like the one you see on the left here, and then run an antenna check detecting all vulnerable sinks, and then we only replace fake diodes with real diodes on those things that were deemed vulnerable. Of course, this removes the two of the cons that we had previously, eliminating the unnecessary capacitive load, but one of the cons still remains, so we still have a limit on the maximum achievable core utilization because we need to reserve the space for all diodes in advance. So of course it would be nice if we could only insert diodes as needed, but this requires antenna aware tools, and the technique here is to insert diodes only when needed on the vulnerable sinks during global routing. This is already implemented in FastRoute and is being used, but is not 100% stable on Sky 130. And finally, after physical implementation, we extract parasitics from the layout using the SPEF extractor, which is a CloudV project, and then run static timing analysis on the routed layout, followed by physical verification, which are DRC and LVS using Magic and NetGen, plus antenna checks using either Magic or Antenna Rule Checker within the OpenRoad app. and if everything's fine, we stream this using magic into GDS2. So I have not mentioned what synthesis exploration or design exploration are, so I will talk about those briefly. So synthesis exploration is the process of running the design through the available synthesis strategies in OpenLANE, and it gives you a visual representation of the area versus delay relation. So for example, this is an HTML dashboard that is generated for one of the designs comparing the 4 default synthesis strategies. The user can of course add their own synthesis strategies if they know how to write ABC scripts, and this helps the user to pick the netlist that achieves the right area delay balance for their application. A similar idea can be applied flow-wide by sweeping different sets of configuration parameters and inspecting the resulting layouts. This is helpful to find the optimal set of values for some of the configuration parameters, like the optimal core utilization and placement densities, and so on. We commonly use these techniques to ensure that there is an optimal set of configuration parameters for each design of our design test set of around 40 designs, which can be seen on this link that is on the screen. So here is a list of the standard cell libraries in the SkyWater PDK, as well as their current status and compatibility with OpenLANE. The ones that have an asterisk next to them means they have a sheet on our repo under benchmark results on the link that you see down there. Every sheet lists around 40 designs, and stable here means that most of these designs finish DRC clean and LVS clean. Unstable means that some designs or many designs might be failing under this library, and under test means that there isn't a corresponding sheet yet. So if we have a look at one of the sheets, say for the HD library, there is a lot of data about their running time, utilizations, memory use, cell count, number of violations, number of LVS errors, number of antenna violations. The reason we're storing this data directly on the repo is to make sure that every commit that is marked as stable can produce a sheet equivalent or better than the previous one. So this ensures that the quality of results is always improving on average. And now we get to talk about the SoC integration flow. I'm going to use the diagram on the right to guide me through the next few slides. The first step in the process is to make sure that all macros in the design are routable. Soft macros are by definition routable because they were produced already by OpenLANE, and therefore they join later in the process. For third-party macros, which are usually developed independently with none of the tools used in OpenLANE usually in mind, and those include I/O pads, analog blocks, or SRAM blocks, for example. So for that purpose, there are scripts to help wrapping and or abstracting third-party macros for use with OpenLANE, and this is actually a very well invested one-time effort. And an example is the SRAM 1 kilobyte block compiled by OpenRAM that you see here, which was used in 2 of the chips, the OpenRAM test chip and Strive 2. So this is how the abstraction procedure looks like. So here, for example, it extends the pins that are going to be used slightly outside the boundaries of the macro and obstructs everything inside on the layers used within the macro. And now the routers can only process the clean abstract view instead of the billions of shapes of the details that the router doesn't need to know about. So an added benefit is reduced running time. Another added benefit is that this divides and conquers the problems of DRC and LVS. And since most of the time one will use a hard macro that has already been verified independently, this abstraction allows us to already make use of this information and be able to run DRC and LVS with the abstract view of the macro. Since these obstructions are conservative, this means that the router should not and will not interfere with anything going inside the macro, and so running LVS and DRC with the abstract view yields accurate results. Still, a full DRC and a full LVS are still important and should be done as sign-off checks. The next step is the generation of top-level description. And this is an optional step and is intended for users who are unfamiliar with I/O pads, who would provide their design, and the tool would generate a top-level structural Verilog containing the user design and interacting with the pad frame. Then we can go ahead and generate a pad frame. We have a couple of pad frame generators. The first one, which was written by Tim Edwards, is the one we have used so far for our chips. We have another version based on OpenDB, which incorporates already many of the ideas in the original one, but avoids some of the issues we had with it. The output of this step is the layout of the pad frame with the various views, as well as a SPICE netlist, which can be used to electrically simulate the pad frame, as well as test its resilience against ESD effects. Before we move on to the next steps, I'm going to revisit the learnings we got from the first drive chip to motivate the ideas I'm going to introduce. Top-level routing output by OpenLANE of the first drive chip was unclean. There were many DRC errors that had to be fixed by hand, and there were many issues like shorts. It wasn't LVS clean out of the box. So when analyzed, these unclean routes had two root causes. First one is the many macro to macro nets on the top level, which were causing congestion, which can be already clearly seen in various areas of the chip. Another main reason is the suboptimal placement of the I/O pins on each of the macros. Because remember, each of these macros were hardened independently from the rest and without knowledge about where they're going to be placed next in a bigger design. Another issue was that the power routes had to be done manually by hand for lack of a tool that could do chip level power routing. So in tackling the first issue, we know that the less nets there are on the top level, the less the routing resources are going to be needed, of course. So repartitioning a design to have less, or ideally as recommended, a single core module will help greatly in reducing congestion. The next issue causing congestion on the top level is badly placing macro pins away from other nodes on their nets, wasting valuable routing resources. And we have only 5 usable metal layers on the top level, so this would cause surely congestion and many problems. But again, the issue is that the tools work bottom-up, not top-down, and that knowledge of how a macro connects externally is not available while hardening such a macro. The idea here, which is the basis of a custom tool we have, is to do what we call contextual floor planning. It can be used to create a virtual floor plan of the macro being hardened that shows it in the context of its instantiation, as you can see here in the picture. And based on that, one can run various context-aware steps of the flow, like we do context-aware I/O placement here to handle the problem at hand. And now, since the I/O pin locations were optimized based on how the pins connect to the outside, we expect the signals outside to be almost straight lines, as you can see here by the dotted lines. For the last issue of flagging a tool to route power to our chip macros, we have developed a top-level power router with the sole purpose of hooking up macros to power pads. Some assumptions here are the implementation of the recommended hierarchies. The macros should also be hardened with concentric power rings around the boundaries, and the power router would attempt to use the highest metal layers available and maximize the number of vias in transitions between layers to connect the power pads to those core rings. This is of course to reduce the IR drop. The power routes are DRC correct by construction, so there was no need to implement DRC checking in the tool. So now that we have listed all of the components we needed, this is how a theoretical power routed chip floor plan would look like, with the core module in the center having 2 concentric power rings with the pins context aware placed so that they face the pads or the macros they are connecting to. The chip would be also pre-power routed before signal routing and would be ready for the next 2 stages, ending with physical verification and the streaming of GDS2. So here is a more realistic version of this figure. This is Strive 2A, a fully automated member of the Strive family. As you can see, most of the signal routes are mostly straight lines, and it's pre-hooked up to power. And in fact, the time to harden everything from scratch and assemble this chip is around 57 minutes. Most of it is taken to harden the individual macros that you see here and the core macro. And the chip assembly itself, in fact, takes around 5 to 10 minutes. The final layout is LVS clean, and there are no real DRC errors seen by open source tools. So TryToRoute reports 0 DRC errors. Magic doesn't report real DRC errors. So some final remarks are now in order. So we note that the SoC release alongside a sample chip, Strike 2A, is pending the open source release of the IO library, which should be happening soon. And that OpenLANE is currently the only open source flow that can be readily used to almost fully automate chip assembly. And I'm saying almost because there are still antenna issues. They are not gating issues, but they are nevertheless issues to be worked on. Also, OpenLANE is planned for use in the upcoming public November shuttle. So when it comes to future and ongoing work, which the community is always welcome to contribute to, we note that the recommended hierarchy is not ideal for all use cases, so we would need to work around the cons of the current hierarchy when it comes to multi-voltage domains. We also need to adapt some of the features to work with Caravel. So the first point, for example, is something that we need to work around. We also would hope to target 0 or as close to 0 antenna violations as possible, because the FastRoute antenna avoidance flow currently is not perfect, and the closest to 0 are the two strategies, the spray and pray strategy and the fake diode strategy. Finally, we would like to thank everyone who contributed to this project. This project would not have been possible without the contributions of many people, including Tim Edwards, Karim Farid, Ahmed Ghazy, and Mohamed Ghazy. And that's it for my presentation. I'm looking forward to your questions during the workshop sessions, and thanks for listening.